Today we will talk about another model which was advanced by Dobbins in 1956, and it was an effort to attempt to explain the KL average DAB relationship with exponent somewhere between 0.5 and 1. We had seen yesterday that penetration model or surface renewal model, or for that matter any model for the renewal of surface, will lead to the diffusivity to the power 0.5, much better than the film model, but then there are these exponents ranging from 0 to 0.8 to 0.9. So, the curiosity was it possible to get an exponent between 0.5 and 1, and when we look at literature even below 0.5, it called for a paradigm different from any of these single parameter models. Dobbins thought that if we combine the features of film model and the surface renewal model, namely the infinite time presumed to be available in film model leading to steady state, and the infinite extent of an element of liquid assumed in the surface renewal model. So, his idea was, what if we combine renewal with a finite extent like thickness of the film, the parameter of film model, and renewal, which means a parameter which is fractional surface renewal rate, or small s, which we found appeared in the stationary age distribution function s e power minus s theta. So, he attempted the analysis taking elements of the surface renewal model of finite thickness. He called it ZB, z equal to z tending to infinity, c equal to c s 0, which is the boundary condition in the penetration or surface renewal model. He replaced by z equal to ZB like the film thickness, at the end of which the concentration is now the initial concentration. So, when you do this and you take into account the renewal, one thing is clear right at the outset, that now we have two parameters, the film thickness and the surface renewal rate S, ZB and S. It turns out, and maybe let me make this as your next assignment, derive this equation for KL average under the assumption that the elements in surface renewal model have a finite thickness ZB. Rest everything is identical as in the surface renewal model or the penetration model. Is that clear? You get about a week, and that also implies that in this week's time it becomes mandatory that you learn Laplace transforms and even use it to solve this problem. You know something about Laplace transform, right?
Yeah.
All, that's all third time. So, that is not going to be very difficult. Having said that, I made one comment, if you have registered that, I said that infinite domain problems are easier to solve by Laplace transforms, then and the finite domain problems will be much harder, and you do see that difficulty. So, good that you have some exposure to Laplace transforms repeated, and now this will be third time, and hopefully you will learn something new here. I have timed this assignment also to ensure that we discuss one particular problem in context of penetration model, which goes along that line that the equations contain a lot of information, we have to be perceptive enough to draw it out of it. One example of this was when I introduced you to similar transformation here, and I made it clear that we have a method which is a very simple method based on dimensionless considerations or dimensional considerations, which allows you not to remember similar transformation, right. You can figure it out. So, the information is already there in the equation, you should know how to tap that out. The equations must speak to you. So, there is another problem which is a variation of the mass transfer in the context of penetration theory. We hopefully will find some time to talk about today. Okay. Before I do that, let me complete this discussion and then we come one step back and resume with penetration theory and that particular interesting problem I need you to think about. So, it turns out that finally, when you get the KL average, it works out to be dependent on S and ZB, and we have the mass transfer coefficient coming from the surface renewal model root DABS identically appearing here as a coefficient. And then we have cot hyperbolic function, and obviously the argument has to be dimensionless. You see that root of S ZB square, S is time inverse, ZB square is length square. So, length square by time, this is length square by time. So, that is dimensionless. Okay. Now, from here as yet we can only see that Dobbins had succeeded, and you will verify, in combining the features of surface renewal with the finite extent of film. So, we do have these two parameters. Question is, does it fulfill our expectation or what Dobbins intended initially? Does this tell us where how, for example, KL average would be possibly varying with DAB to the power which is between 0.5 and 1. So, to do that, you could think of one more dimensionless number. We will not name it right now. This is KL average. If we divide this KL average with the mass transfer coefficient you first derived yourself, that was in the case of diffusion in a solid membrane, non-porous membrane. That was DAB by delta, here it will be DAB by ZB. That is the film theory's film transfer coefficient, ratio of diffusivity to the film thickness. So, if you divide this by DAB by ZB, left hand side is dimensionless, and this then could be plotted as a function of, let us say, this parameter. Okay. When you do that, you would see when S ZB square by DAB is small, when S ZB square by DAB is small, this is cot hyperbolic of a small quantity, that is going to be the reciprocal of that small quantity, right. So, you multiply basically this by reciprocal of this. So, that gives you root DABS into root of DAB by S ZB square. So, this S cancels, root S cancels, this becomes DAB and this is ZB, right. So, KL average is DAB by ZB as expected from film theory. So, when you have this argument, this square root of S ZB square by DAB is small, you are approaching film theory. What it means is basically, when is this likely to be small? 1, when S is small, surface renewal rate is small, that means the element is rarely replaced. If it is never replaced, it is film theory, steady state, or rapid penetration. DAB is large, so the steady state is attained quickly, right. Those are the conditions. Slow renewal or rapid penetration, small s or large DAB will be conducive to having our two parameter Dobbins model converge onto the film model. Now, what would happen if the reverse is the case? If the renewal rate is rapid or the penetration is slow, diffusivity is small. If S is large or DAB is small, then this number is large. At this point, some trigonometry, hyperbolic trigonometric functions plots could come to your mind. If you remember how tan hyperbolic of some quantity chi would vary, you know that it goes like this. When the argument becomes moderately large, the tan hyperbolic converges or approaches 1. So, when this quantity is large, tan hyperbolic is 1, cot hyperbolic is 1, you get KL average equal to the transfer coefficient coming from surface renewal rate, right. Graphically, you could represent this as here KL by DAB by ZB, the dimensionless mass transfer coefficient shown as the ordinate, and root of SZB square by DAB shown as abscissa would give you this plot. When this number, this dimensionless group is small, SZB square by DAB, you approach film theory with exponent of 1 in KL average proportionality to DAB to the power n, n is 1, and when this becomes larger than about 3, we reach the other asymptote, KL average goes as root DAB s. So, in between you have those exponents between 0.5 and 1. So, this is a greater achievement, but it has come at a greater cost, because instead of the single parameter, now we have to deal with 2 parameter S and ZB. Okay. Now, it will make a little more sense to what I was saying. As you accommodate more parameters, you can explain more things, you can describe more things. Okay. Next question out of curiosity might come, is it possible likewise to go to the exponents which are between 0 and 0.5? We got 1, we got 0.5, we got the whole range of 0.5 to 1 at the expense of one extra parameter, and then next question would come, is it possible to go under 0.5, between 0 and 0.5? This was exactly the question which was answered by C. Judson King in 1966. He combined the surface renewal theory with one of the things which came up as a part of question, and that time I said that we will keep eddy diffusion away. It was too early to talk of eddy diffusion then, but exactly that piece of information is required. You need to take into account the eddies coming to the surface and eddies reaching right up to the surface, but not entirely unhindered, because there is surface tension operative at the liquid gas interface. The eddies could be dampened a bit. So, by combining the features of surface renewal theory and the dampening of the eddies near the surface, that means diminishing value of eddy, Judson King could demonstrate that exponents less than 0.5 are explainable. Okay. Surely you require extra parameter. Yeah, before I go into surface stretch theory, now I want to take that step back. Forget about the slide now for the time being. Okay. And I want you to now become interactive. Let us try and write equations corresponding to surface renewal model, or let us say the penetration model, because that is the integral part of the surface renewal. We borrow that directly in terms of Na theta, the instantaneous flux. The question we asked is the same question we had in the first problem. What if a first order chemical reaction accompanies diffusion? You get that? So, the problem is same, except that we will have now introduced a first order reaction of the diffusing gas. Okay. So, let us see what we have. We have the gas bubble rising with velocity UB. We have an element of liquid which rolls down to the lowest position, stays in contact with this gas and absorbs A, and here it is released to merge with the bulk, and this time of contact, say theta, as dB by UB, diameter of bubble by rise velocity of bubble, is short, and it is, for the simplicity, let us take only one passage like this element of liquid sticking to gas bubble right up to this lowest point. Okay. During this short time, diffusion takes place in unsteady state fashion, and now what we are saying is A, which is the species within the bubble which is diffusing and getting absorbed into this liquid, is also reacting. Okay. So, let us write our equations. Unsteady state diffusion will be given by dou C A by dou theta, theta is time. Let us say we have dAB dou 2 C A by dou Z square. We have Z measured from the interface into the depth of liquid, into the element. Okay. Accumulation, unsteady state term, diffusion, and we are saying that there is something more happening. As A gets into the liquid, it reacts with the liquid to form some product or products by a reaction which is volumetric and first order. A reacts with the liquid in the element, forms certain product or products, we do not worry, it is irreversible reaction, first order. So, K1 volumetric, so I am putting triple prime. Volumetric means for this reaction to occur, it would require volume. Bulk reactions or volumetric reactions are distinct from surface reaction. They could both be of whatever order. Okay. Here we are taking a volumetric reaction. Now, this was the original equation. Since we introduce reaction, we must have loss of A, and that will be given by this term minus K1 triple prime C A, right. Are the units consistent? Always think in terms of dimension. Left hand side is concentration by time, right. So, left hand side units are concentration by time. DAP and Z square in denominator position leaves second inverse, because DAB is meter square per second, Z square goes as meter square. So, we left with second inverse. Numerator is concentration. So, concentration by time is perfect. What about the last term? We have concentration there, first order reaction rate, volumetric. So, the units are second inverse, first order decay, time inverse. So, concentration by time, everything is fine. So, this equation is okay, all right. Now, let us come to the conditions. When the element comes to the top of the bubble first time, that is where time begins, theta equal to 0. At that time, the concentration everywhere within that element will be C A 0 for all Z greater than 0. At theta equal to 0 also, but Z equal to 0 we are excluding that interface because we want it to be saturation. Okay. This is the initial condition. What is the other condition? At Z equal to 0, for all theta greater than or equal to 0, the concentration is saturation concentration, interface concentration CAI. Can you all see this, what I am writing? I am sure of my slides fonts, but here. Okay. We are working with the penetration paradigm. So, we can think of Z tending to infinity. Originally, the condition was for Z tending to infinity, for all theta greater than or equal to 0, the concentration was unaffected by diffusion and it was C S 0. Does it complete the statement of our problem? Is it now a well posed problem? Can react. So, that last condition cannot be right. So, how do we modify that? Clearly, what I have written as last condition is not correct, because A present there, if it were 0 it would be another matter, but if it is any finite concentration it could react, that is it. So, we should actually be writing the last condition as Z tending to infinity for all times, the concentration should be dropping. And how does it drop? Our argument that at Z tending to infinity diffusion does not play a part, which means we could go back to our governing equation, we could drop that term for that region, and then this is nothing but dCA by d theta equal to minus K1 triple prime Ca. The first order K1 triple prime Ca is the loss. Whatever it is there, whatever A is present at any location at any time, it could react according to this equation. If diffusion is influencing that region, we have to take that term. If you are taking the region to be far away from the action of diffusion, towards infinity diffusion does not affect anything, we will be dropping this term, and then we say dCA by d theta equal to minus K1 triple prime Ca, which admits a solution Ca 0 e power minus K1 triple prime theta, first order decay. So, we should be writing here exponential minus K1 triple prime theta. Okay. This is what I meant. I am saying that you do not even have to remember how the concentration decreases by a first order reaction. We get that from here. So, the information is there in the equation. We must know how to communicate with it. In the region far away from the interface, diffusion cannot alter anything. So, this term cannot be there. So, we just solve this, this is the solution. Okay. Now, you could go a step further, I will let you do this. I am interweaving the concepts, understanding and some work at home for you, but not without some clues here. New formulation for the diffusion reaction equation, first order reaction equation. If we had to solve this and obtain the concentration profile first and then the instantaneous mass transfer coefficient, then the average mass transfer coefficient etcetera, amount absorbed, can we use similar transformation now? If we use the same similar transformation as earlier, what would be a potential difficulty? We would not be able to collapse condition 1 and 3 into 1, that cannot happen. Besides this, because of that term, we would not be able to cancel free z and theta from your equation. So, it can't be expressed as an ordinary differential equation in independent variable eta combining z and theta. So, this is an appropriate case. Similar transformation cannot solve this problem. So, we have to go for the Laplace transforms. Okay. So, I will give you some ideas here. We have two independent variables z and theta, and you remember that Laplace transformation, let us say C A bar will be integral from 0 to infinity e power minus p t C A or p theta C A z theta d theta. Alternatively, since z goes to infinity, one could have thought of doing the Laplace transformation with respect to z. If you attempt that, you would see there is a problem, because we do not have the boundary conditions corresponding to that approach. So, it works out we have to choose to transform the concentration profile C A z theta with respect to theta. So, when we have done this transformation, theta will be integrated out. After we do this transformation, C A bar will no longer be dependent on theta, it will only depend on z. So, the new dependent variable from the original C A theta z we get is C A bar of z, and therefore, the governing equation would become an ordinary differential equation. But the question arises, what do we mean by taking Laplace transform of an equation? So far, perhaps I presume that you have thought of Laplace transform, taking Laplace transform of a function. I am talking of now taking a Laplace transform of an equation. The question is, what do you understand by taking Laplace transform of an equation? Be specific. We have an equation on hand. I want to take Laplace transform of this equation. What should I do? Steps. No, much simpler than that. Multiply each term on each side by e power minus p theta, each term by e power minus p theta d theta, and then integrate. So, each term will be transformed. Okay. It will be transformed, that we will find out, right. The first step is, therefore, take your equation multiplied by e power minus p theta, which is known as kernel of Laplace transform, and d theta, and then integrate each term. That will be what we will mean by Laplace transforming an equation here. Now, let us think of doing that. I told you that I will nudge you towards learning Laplace transform. Whatever is not clear here, you can go back to the fundamentals, brush up the definitions and theorems, and they should become obvious. So, multiply by exponential minus p theta d theta here, exponential minus p theta d theta, exponential minus p theta d theta, and then integrate from 0 to infinity. If we define Laplace transform of C A this way, C A multiplied by e power minus p theta d theta integrated from 0 to infinity. If it is C A bar, then in this equation during the process of transformation, which is the simplest term to write as next step? Simplest is this, there is nothing we are doing. K1 triple prime is constant, we take it out, and then it is C A bar, right. And this C A bar, because we integrated time out, theta out, will only depend on z, correct. Next term is something over here or over here. Which one? Your choice. This one? Okay. I thought it was the first term on the right hand side, which is easier. And why? I do not even have to do this integration by parts or remember anything about it. Here I have to know something fundamental about calculus. If I had two operations being performed simultaneously, then when can I interchange the order? See, I am differentiating C A first with z and then I am integrating with respect to theta. Differentiation is with respect to z, integration is with respect to theta. These are two operators operating with different independent variables. So, I can interchange the order. So, which means I can put the integral side inside. So, simple again, this C A becomes C A bar, T A B remains outside, and because now C A bar only depends on z, I will write this as d A B d 2 C A bar by d z square, right. And then the most difficult is here, and that you can do by integration by parts, or if you remember what is the Laplace of a derivative. Derivative with respect to same independent variable you are using for transformation. Here it is theta. Does anyone remember that? PCA bar, PCA bar, that is all? Minus something, what is that something? Minus C is 0, right. That is the function value at time 0. So, that is also not difficult, P C A bar minus C A 0. Okay. Once we have this, we have the ordinary differential equation Z, but we can't solve the equation for C A bar until we have transformed the conditions also. In the last step, P C A bar minus C A 0, we have absorbed the initial condition, we already made use of one condition, clear. But these two are still in terms of C A and we need it in terms of C A bar. So, we transform these conditions also. When Z is 0, C A will be Laplace of a constant C A I. What is the Laplace of a constant? Yeah. So, here it will be C A I by P, right, and Laplace of C A 0 e power minus k 1 triple prime theta, C A 0 by k triple prime only, P plus, it is P minus k 1 triple prime. So, P plus k 1 triple prime. K 1 triple prime and P, remember, have the same dimensions, time inverse. So, they can come together in P plus k 1 triple prime. Okay. So, we have two boundary conditions, we have the ordinary differential equation C A bar, you can solve it. This part is straightforward, this is a simpler phase of your analysis. Okay. Transforming, solving the ordinary differential equation is the easier part, but we engineers are creative, we make use of all the efforts of people from other sciences, especially mathematicians. So, the more difficult part always in dealing with Laplace transformation is inversion from C A bar to C A domain, going from C A bar P z to C A theta z, inversion. And I told you that z equal to infinity, z tending to infinity is the easier case. So, we can make use of tables. Okay. Maybe I can ask you a very simple question, what are the longest tables of Laplace transforms, functions and Laplace transforms you have seen ever? 6 entries, is that all? 36 functions and Laplace transforms. I heard 6, I thought it was too short. Guess what is the longest compilation of Laplace transforms might exist in the history of mathematics? 1000? 20,000, bit of overestimate. 15,000 entries. Roberts and Kaufman compiled a long enough table, 15,000 entries, f thetas and f p's, and practically everything that you need to invert can be brought down to one of the entries, and then it is easy for you, right. They spend their lifetime, you can submit assignment within a week. Okay. That is how it is. Having said that, you still will need the relevant table. So, hopefully by Monday I should be able to email it to you, or no, the short one, the more relevant one, because I give you Roberts and Kaufman, you will be lost. But it will not be like directly whatever you require will be available in that table. You still need to make use of shifting theorem, okay, the common properties of Laplace transforms, but you should be able to organize it. And I would say, why did I say till Monday? Because till then I want you to search the tables yourself, which is basically trying to tell you that it is important to go to library. Even today, everything might be available at your fingertips through internet, but it is still important to go to the library and look at books. One of the orthodox ways of going about this course is that I would want you to go back to the books yourself. It is fast becoming a lost habit. Nobody reads books these days, overwhelming majority of people, and that is something you should not. In last 100,000 years of our evolution, certain basic things have not changed, and learning from books still remains. One of the reasons I do not give you the slides is because I want you to not lose the art of notes taking. You should be able to write down the most essential things, maybe in a shorthand, whatever. See, the brain hand coordination still plays a very important role. Somehow that does not translate in operating with the keyboard. I do not know how it is, but that is how it is. Okay. So, till Monday search on your own to solve this problem with the tables available. By Monday evening, whether you got it or not, I will make sure that you receive this table, and then after that you still get enough time to take from that limited selection appropriate entries and get the concentration profile for diffusion with chemical reaction under the short time of contact or unsteady state consideration. Getting concentration profile is not sufficient. Obtain the flux and therefore the instantaneous mass transfer coefficient, obtain the average mass transfer coefficient and the amount of gas absorbed in a given time. All those, whatever you do in absence of reaction, whatever is given in treble, those corresponding expressions with reaction you should get. In the process, also see whether you can define certain dimensionless group like the one you had derived in the solid membrane diffusion problem case. Okay. There should be something more to that because of chemical reaction. Okay, that leaves me with 5 minutes to finish the surface stretch theory, which does not merit more time here. Lightfoot here is same from your bird-steered Lightfoot. Lightfoot's group contributed to the mass transfer models when under certain set of conditions you have an oscillating shape. like of a drop or a bubble. Maybe I can ask you a question. Have you seen ever a single bubble rising through a column of water? Single bubble? Never? Maybe watch it. If you are not in the aquarium, you have too many bubbles rising, right? But if you, even if you release, let us say you have tall glass column filled up with water, and at the bottom you release a single bubble at the along the axis. It turns out the bubble never goes along the axis in a rectilinear fashion. Rather, what happens is it meanders around the axis and goes in that wavy way. The question to you is, why would a bubble do that? And no matter how carefully you create that bubble, this always happens. What could possibly be reason? Movement of water is not the reason. The column is filled up with water which is stagnant, quiescent water. You just release a bubble at the bottom and it goes dancing about this axis. The reason is, you tell me, take 10 seconds. Why? I am expecting reason from you. What is that? Fluctuations on surface because of, see, the bubble is still a very large collection, gas phase, but very large collection. If the bubble in a question to suit your answer, if I shrink the bubble to nearly molecular dimensions, then I will have this non-equilibrium situation, Brownian kind of movement. This is not that. The reason is, you never can create a perfectly spherical bubble. Okay. When you create this bubble, it is slightly deformed from sphere, which means along the surface the radius of curvature is changing. Okay. Not concentration. That is the reason why the pressure is changing. Delta P, which is difference in pressure across the interface, is given by 2 gamma by r, but a radius of curvature is changing because it is not exactly spherical. So, the delta P is a difference, so pressure distribution is different. What will bubble do? Bubble will try to attain the equilibrium shape. So, if it is elongated, let us say in vertical direction, it will try to become flatter as a result of the surface tension forces. In the process, it overshoots the equilibrium. So, it becomes longer now in horizontal direction. Yeah. And now, because the pressure is not uniform, this will happen. So, the bubble is subjected to different pressures along different directions. So, it meanders. Okay. Anyway, the point is that I have demonstrated to you reason why we can think of these periodic variations. So, the bubble is longer here in this direction, then it becomes longer in this direction, keeps on happening, and it can happen for drops and bubbles with certain periodicity. So, in so many cases we have two phase or multi phase contact, and we have to create phases in the form of droplets. This is a very common phenomenon. So, Lightfoot's group looked at this situation and they advanced this surface stretch theory, like say for example, acetic acid being is diffusing into ethyl acetate drop, which is rising through aqueous solution of acetic acid. So, according to them, this is what happens when it gets flattened or elongated. In the core, there is mixing happening, and the transfer is taking place between the outside and the core across a thickness which is changing, and is changing periodically. So, if you can quantify that periodicity or oscillation, then KL average according to them is given by A divided by AR. A is instantaneous area, AR is some reference area which is defined for each particular situation, root DAB by pi theta r, where theta r is a constant with dimensions of time, like for example, the formation of a drop. Okay. See, the form of this is similar to the penetration model's mass transfer coefficient, and this is weighted by root of integral from 0 to theta by theta r A by A r square d theta. So, this is how for many situations the integral can be evaluated once the periodic nature of variation of area is known. Once that is known, then this can be calculated. So, this is the equation which comes from Lightfoot's group as surface stress theory. In the next class, which will be tomorrow, I suppose, we will look at yet another appearance of similarity transformation, but somewhat harder than the first one. And it is because now the mass transfer does not happen at the free surface in a film, but near the wall, and the velocity is no longer taken constant, but most rapidly varying, could be taken as a linear variation, and we can use this kind of approach for tube flow also. So, that is Grace-Nussel theory for you. We will take it up tomorrow. Stop here.